Now, continuing talking about linear systems of equations, we finished by talking about the elementary row operations where we can switch rows. And now I wanted to put it all together, and because I was tired of talking last video. Now, so let's do an example of what happens in this situation. Let's do an example of how to solve one of these systems of equations. Okay. Actually, change your mind. We're not going to solve systems of equations in this section in 1.2. Reason being, there's easier ways to deal with this called matrices. So we're not going to finish. We're going to conclude 1.2 and actually not going to continue at that point. So what I want to stick it out now is matrices, which is probably more important, which is probably the most important thing in this chapter, because we use matrices a heck of a lot through this book. So it's something we really want to understand. Okay. So we're going on to section 1.3. Okay. And a matrix yes, blue pill or red pill, which would you like? But neither of these have anything to do with matrices, at least in the mathematical sense of what we want to talk about. So matrix, a simple definition that I'm going to give you, is an array right. Is simply an array of data. So I can collect it. It takes rectangular forms, triangular forms. There's various ways we'll talk about that. But in general, and I speak of a matrix, I speak of an array of data. Okay. And a matrix. Okay, a matrix does have certain characteristics. Okay. Alright, simply an array of data. Your book gives a much more complicated definition, but I would rather not use that. It's simply an array of data. It has certain characteristics, and we'll talk about what they are. Here, in this piece of the puzzle, we denote them with capital letters. So, we denote them with capital letters such as A, B, C, etc. Right? We denote them, that's one characteristic. Another characteristic of it is we call their n by n matrices. That's pronounced m by n. meaning we have m rows and columns. I can't spell, so deal with it. Okay. Now, and of course, this is right. Now we have an n and column. Recall that we have in a system of equations, we have the m representing the number of equations and n represents the number of variables. Same situation here. The number of rows represents the number of equations. The number of columns represents the number of variables. So I'll write that. Excuse me. Number of variables. Okay. Here, let me fix my spelling, lest somebody try to shoot me. Okay. There's no complaints that Mr. Butler does not know how to spell. Okay, there. Now, let it fix. Okay. Okay, and usually we represent it with these rectangular braces. So matrix A can be represented like this. And then you have A sub 1, 1, A sub 2, 2, all the way A sub 1, 2, A sub 1, n, A2, 1, all the way to A2, n, A sub m, A sub 1, n, and this is all the way to. And that's how you represent the matrix, so it looks like that with those rectangular braces around it. Okay. And then they give some rows and column definitions that are notations in the book, which I normally don't use when I'm teaching this. So we're not going to use them. If we want to donate a row, we'll donate it. If we want to donate a row, we'll call it simply R1. And if we want to donate a column, we'll simply call it C1, C2, C3, so on and so forth. Okay. And so how do we use that to set up a systems of So how do we use this to set up a systems of equations, you might ask? Okay, fine enough. So I will show you how this works. As soon as I release my nose from all this torture. Okay. So how will we set up a matrix? It's been a while since we've done these, of course. So for example, if I have something like this, so how will we set up a matrix for this? So we set up what we call the coefficient matrix, which just involves the numbers. Okay. So we set up a matrix which will look like this. So the matrix would look like this. Then of course we put a dashed line to separate the answers. Okay. So that's how we set up a matrix. This is called augmented matrix, by the way. Augmented matrix has both the coefficients of the variables and, of course, the answers or the solutions on the other side. Okay? Or the constants, isn't the way to call it. Now, the same row elementary operations apply in matrices. So we can add the rows together. We can switch the rows, of course. Where's my 10? There it is over here. So the row operations. We can switch the rows. We can multiply by a non-zero, or we can add the rows together. At any multiple, which is 9. 0. So let's solve this hideous equation here, which I made up. So the solution might not be very pretty. Okay. So the solution to this problem is not going to be pretty, just warning you ahead of time, since I made up the numbers off the top of my head. So it will not be pretty. So let's take a look at this problem. So how do we do that? Okay. So first, by taking a look at the augmented matrix, which we'll write on this side, going back aboard, we can look at the problem. We can say we have 3, 5, -4, 1. Then we have 2, 7, -3, and 3. And of course, lastly, we have 1, 1. We have 1, 1, 2, and 4. Now, for the sake of showing you by example, I'm going to write up my work. As I go on, I'm not going to do that because it takes up way too much space to do. I like to write it out so you can see what's happening. Okay. Now, recall the rules. We can switch them. We can add them. We can multiply to non-zeros. And our goal is to eliminate every variable. So our goal is to eliminate the variables here, 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 and here, here and there. So our goal, when we're solving matrices, we call triangular form, which we'll go into more detail about in another section. But for now, our goal is to get ones here, here, and here. Okay? And then zeros everywhere else. So we can have infinite ways we can go about it. I like to solve inside out. So we'll solve for letter Z first. Okay. So simply put, if I take this you kind of have this kind of an intuition in this situation you can do. Okay, if I multiply the second row by -1 and I multiply the third row by -1 and add them together, I will be able to get my 1 in this row here and replace it with row 3. Okay, and then we can start by eliminating stuff to get things nice and pretty. Okay. So we have negative row 2 plus negative row 3. And we're going to replace it into row 3. Okay. And again, because I'm trying to, for the sake of showing you what's going on, for the sake of simplicity, we add them together. It says -3, -8, +1, -7. So now, in the future, I may not write all this work out, but for the sake of showing you, it's now this new row that we added together becomes the new row 3, which we'll use red for, I suppose. Now, we need to try to get zeros everywhere else. Okay? So the next way to do that is, well, we can multiply the bottom row by 3 and add them together and replace row 2. So we can do that. You see you have a negative 3 here, and if I multiply by 3, I can get a 0 and replace it into row 2. So we'll do that next. So R2 plus 3R3 replace into row 2. Again, I'm writing way more work than I would normally do. So becomes 2, 7, negative 3. 3, R2 you leave alone. R3 we're multiplying by 3. So let's use a different color for that. Let's use purple, I guess. So 3 times negative 3 is negative 9. 3 times negative 8 is negative 24. 3 times 1 is, of course, 3. And, of course, 3 times negative 7 is negative 21. Adding them together, you get 0. 7 minus 24 should be 17, negative. So should be negative 17. 2 minus 9 is, of course, negative 7. And then this will be negative 18. This new row will replace row 2. So we're calling from our earlier problem, 3, 5, negative 4, and 1. Then our new row 2, to denote with our color purple, which is negative 7, negative 17, 0, and negative 18. And this time row 3, which we left alone, we'll leave it in color red, because it's new and it's not confused with its old counterpart. This which we left alone this time, which was negative 8, negative 3, negative 8, 1, and negative 7. Okay. Now we need to get another 0. Now we need to get another 0 in either it doesn't, again, I like to work inside out. So we're going to get a 0 right over here in that top row, in this top row. So we're going to multiply the bottom row. This is a negative 4, by the way. So we're going to multiply the bottom row by 4 and then add it to row 1. And we're going to replace row 1. Okay. This formal process is called Gauss-Jordan elimination, but let's talk more. But I don't need to sit and define that for you because you've learned this already. So now, there it is. So we're going to take the next row operation here is going to be R1 plus 4 R3 replace row 1. Okay. So now, so 3, 5, negative 4, 1. We'll multiply the next row by 4. Choose a different color, let's say blue. And we'll use that blue to replace. 4R3 becomes negative 12, negative 32, 4, negative 28. Adding them all together, we get 0. So 12 is negative 9. 5 minus 32 will be 27, negative 27. And this ends at this is a negative 27. And from here, because we have a common multiple of 9 that's involved here, let's go ahead and cheat and divide by negative, multiply by 1/9. So to do that, you guys are you guys are relatively smart algebraically. Now, so that means if I do that, I end up with all the negative signs going away. So I end up with 1, 3, 0, and 3 here. And this is my new row 1. So this will become a new row 1. With 1, 3, 0. Three. We end up with negative 7, negative 17, 0, negative 18, with negative 3, negative 8, 1, and negative 7. Okay? Now, we need to work inward here, because now we've done the eliminated 2, 0, now we need to eliminate the middle row here. So to eliminate the middle row here, what do? Is multiply it. Multiply the bottom row by 3, the third row by 3, the first row by 8. So this becomes Another way, although another way to do this, if you want to stop for a second and look at this, is you can see that in rows 1 and 2, that I have the two variables I need to eliminate. From here, I can just eliminate one and actually start to begin to solve the problem. So instead of doing this, which we could normally do, I have to stop it. I'll stop myself right here in the middle of a process to point out a point. At this point, I have to. I almost am done with that problem here. With that piece of the puzzle. So what I need to do is do the last piece here. Okay. Hey. But I'm pointing that out. You could go that direction. You don't have to, but you could. So back to what we were doing. So it's going to be okay. So 8R1 do 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 do. Okay. Progress, yes. Now from here, we need to eliminate the 0 that's in this row here. So we can do that. So we need to make another 0 right about here. These problems take forever, so I'm not gonna assign 1,000 of them, just 2,000. So from here, it should be 8, 3, 17, 51. So we're going to take replace it into row 1. So 17R1 becomes 17, 51, 0, 51, 3, 2 is negative 21, 51, negative 0, it'll be 24, 18 times 3 is negative 54, so we end up with negative 4, 0, 0, negative 3. Yes! Now we have a problem. Now we have a solution. Here, if we divide by negative 4, so we end up with 1, 0, 0, and 3/4. And this actually goes into row 1. Ooh la la. Finally, we're getting somewhere. And so if we add, so now if we finally, now that we're getting somewhere, if we add row 1 and row 2, we can add row 1 and row 3, replace into row 3, and we end up with the solution for there too. So we end up with 1, 0, 0, 3/4, negative 1, 0, 3. We'll just switch it already. 12 over 4. 0, 0, 3. 3 plus 12 is 15 divided by 4. If I divide by 3, divide by 3, that's simple 5 over 4. So 0, 0, 1, and 5/4. Replace that. Okay. Almost done. One more. So we multiply the top row by 7, add it to row 2, and we get the new row 3. Apologize for making it one color now. It's just I'm lazy and don't feel like changing the color now. So 7R1, this R2, replace row 2. So finally, we end up with 7, 0, 0, 21 divided by 4, negative 7, negative 17, 0. We'll just go ahead and switch it already. 18 times 4 is 72. It's going to be negative 72 over 4. Right. 18, 4, 2, carry the 3 is 72. So doing the algebra, we did with 0, negative 17, 0, and it ends up somewhat nice. 72 minus 21, which will do 51, right? I believe. Yes, it is. So 51 over 4, that's a negative sign, of course. So if I divide by negative 17, 0, 1, 0, negative 3, positive 3/4. So we end up with a solution we actually end up with a fairly nice solution here. Of 0, 0, 1, 3/4, 0. So we end up with x is equal to 3/4, y is equal to 3/4, z is equal to 5/4. Okay. You can write it as a point or the ordered triple. You can write it as an ordered triple like that too. Okay. When you're doing your work, I have the habit of when I'm doing this in private to probably skip some of these steps. You should not. The thing about it is the reason why I'm writing out the row operations, even though I could easily do them in my head and end up with the problem done much faster, and you guys have calculators, you guys can do it relatively quickly on those. The reason why I write it out is so that nothing gets lost. That's the thing about doing it in your head. Sometimes steps get lost. So it's important that when you do these problems that your steps don't get lost. That's why it's important to write it out for at least a little while, or write it out on a set, even if you don't necessarily write it in your full solutions. When you're doing the full solutions for the problems, put a set of scratch work aside where you do the row operations like this, where you write it out, where you write out the algebra for your row operations, even if you don't include it in your final solution necessarily. You could, when you do the problems, you can just write 7r1 plus 7r2 and replace it. But make sure that you have a set aside note, or like a footnote, where you've done the algebra. This way you can go back and check for your mistakes and things like that. Because the last thing you want to happen is something get lost in your mistake and you end up doing something wrong. It happens, even to the best. It happens even to professional mathematicians. Okay, so try not to get your work lost, and we'll see. Okay, your book sticks to a bunch of the various processes of Gauss-Jordan elimination, which you can read on your own. I'm not going to sit and read it to you. It's embarrassing when the teacher reads the book to you, so I'm not going to try to read it to you. Right. So that's on 1.3, and so we have some theorems to talk about. Okay. These are some theorems which I kind of skipped over, which we'll talk about in the next video. So we'll talk about the theorems. We'll talk about theorems in the next video. I have a couple of theorems to go over, and I may do the first one, I may not. We'll see. Okay. Okay. So we have a few. Yes, so we have a few things like that. Alright. Yeah, we'll talk. Yeah, we'll talk more about that later. So we'll do the proofs in the next video. And we might not do the proofs, but we'll go over the theorems and what they mean, basically. In the next video, since they basically skipped it. Since I presume you have some kind of knowledge of how to work with linear equations, since this is linear algebra. This is a 300 level course. So at this point you should know what you're doing. So we'll go over the theorems. We'll go over the theorems in the next video, and we'll talk more later. Pucks.